Greetings once again. Welcome to the 189th session of the online Optom Learning Series, OOLS. And for today's session, we once again would like to welcome back Dr. Liat Gantz. Dr. Liat has been very supportive of our programs as she has joined us back for doing today's session. She's a senior lecturer of optometry and also the director of the Masters of Optometry in Vision Science program at the Hadassah Academic College in Jerusalem, Israel. She's an optometrist with bachelor's degree with a minor BSc in computer science as well. She has done her PhD in vision science in the field of psychophysics of depth perception from the University of Houston College of Optometry. She has also done her postdoctoral training in clinical electrophysiology. And I think she had so much passion that she has done another postdoctoral training in psychophysics of depth perception as well. Actively publishing her research work in peer-reviewed journals, and most likely, or I would say her interests are in the field of depth perception and clinical optometry. And she is also a fellow of the American Academy of Optometry and the European Academy of Optometry as well. And she's going to talk to us today about heterophoria. How should we assess it? What are the methods which should be utilized? And she'll take us through her journey of her understanding as well. So welcome back, Dr. Liat, onto our platform. And let me just, leave the screen time to you.
Thank you, Fakhruddin. Thank you for inviting me again. So I'm going to start from the beginning, and we're going to slowly progress into our talk for today. First, I'd like to welcome everybody. Greetings from Israel. This is a picture of my college, Hadassah Academic College. And this building right here used to be the Rothschild Hospital, which was established in 1888 and functioned as a hospital until 1939. And it has been a home to my college, Hadassah Academic College, since 1970. So I welcome you all, if you ever are in the area, to come visit us. So what we're going to discuss today is, first, we're going to start with what is phoria, what is heterophoria, different measurement techniques. We're going to talk about some studies that compared between the different methods. And we're going to talk about some findings from my own research in which we examined how different aspects of the procedure might affect the outcomes. And then finally, we're going to talk about how it might be clinically relevant to us. So before we begin, Fakhruddin, I'm going to ask you to please put up the polls. I wanted to ask you about how you measure your patient's phoria and whether you measure your patient's phoria regularly.
I think most of them do measure phoria regularly. Almost half of them.
Approximately 50%.
Yeah.
Check their patient's phoria routinely.
Yes, and I think about 44% said that they would do it only when indicated, and about few of them only do for children at this point in time. Yeah.
Okay, so that was the first question, if you regularly measure your patient's phoria. The second question is, when you do measure your patient's phoria, which measurement method do you use?
Great. So I've launched that as well. And if let's say there is some other tests, we have put that option as well. So if let's say you know of other tests, please feel free to put up on the chat what test would you usually use. I think about 65% of them use cover tests, followed by Maddox rod and one graph. Yeah, that's the status of how people measure phoria today. Yeah.
Great. So you've all answered the poll. Let's go back to what is heterophoria, which is also called phoria. And I know you all know this, but I'm just going to go through it anyway, because we all come from different countries and we all studied at different times. So we might as well go back to the basics and then we'll continue from there. So the phoria measures the dissociated eye's position. And by dissociated, we mean when there is no fusional vergence demand. So when we don't demand that the two eyes work together, what is their tendency? And it's measured under conditions that cancel fusion. So if we're talking about cover test, will be covering one of the eyes, and we'll be looking to see what the eye does under the cover when fusion has been canceled. Phoria basically tells us what is the demand for fusional vergence, which means when we measure after we've canceled fusion, we measure what the tendency of the eyes is, then we basically know what the eyes are doing, what they need to overcome when the two eyes are required to cooperate and look together in free space. So it tells us how much effort the muscles exert in order to stay fixated and to stay straight on target. And it's a measure of our motor fusion. It's also called the latent deviation because it's measured when we cancel out fusion and we look at the eye under the cover. So we have orthophoria, and in orthophoria, when we cover the eye just stays in the same location because there is nothing to overcome. The eyes don't deviate and they don't have a tendency to go anywhere. Esophoria, and when the eyes tend to overconverge when there's no demand for fusion, which means that in order to stay straight during the day, motor fusion needs to be diverted in order to stay fixated. And exophoria means that the tendency is for the eye to underconverge or diverge. And so when the two eyes have to function together under normal conditions, fusional vergence has to overcome this tendency to divert. And the majority of the population, we have a tendency for orthophoria at distance and a tendency for a little bit of an exo at near. And this is just, all the different studies show this in different populations around the world. But what's really interesting is that no matter where the study is conducted worldwide, the distribution is a keratotic distribution, which is a distribution that looks like this. It's not Gaussian. It's not a normal distribution. It's keratotic, where it's got like a very distinct peak. So when the fusional vergence system is able to overcome the demand, the phoria is said to be compensated. But if the fusional vergence system has difficulty overcoming the demand, the phoria is said to be decompensated. And that's a tricky and unwanted situation. And if it's not able to overcome the demand all the time, and sensory fusion, meaning the brain is not able to fuse images from the two eyes, then it becomes a strabismus or a squint, becomes a manifest deviation. So how do we measure heterophoria in the clinic? We have several tests. Some are considered subjective, and we have one test that's considered objective. The majority of you said that you use cover test, which is an objective. It's considered an objective clinical test. And in a few minutes, we'll talk about whether it really is objective or not. But let's first concentrate on the subjective tests. The subjective tests can be split up into two different types of main categories: dissimilar image tests and similar image tests, when there's only one that I know of. But perhaps you all use a different test that's not mentioned here that might be a similar image test. So in the dissimilar image test category, we have the Maddox-Rod test. Then we have the Maddox-Rod test in combination with the Thorrington card. We have the Maddox-Wing test, and we have the Schober test. In addition, there's the Howell card, which is really similar to the Thorrington card. And there's another type of test, which I'm going to show you later, which is also it's considered a similar image test. A similar image test is the Von Graff test. And as I mentioned before, the cover test is considered objective. It's a similar image test, but it's completely different from all the subjective tests. So the Maddox-Rod is a combination of plano-convex cylindrical lenses that cause a point light source to appear in visual space as if it's an extended line, typically red in cover when the red Maddox-Rod lens is used. And if we hold the ridges of the Maddox-Rod so that they're horizontal, we obtain a vertical line. If we flip it over so that the stripes are vertical, we obtain a horizontal line, and that measures vertical phoria. When the patient tells us that the red line seen by the right eye is on the left-hand side, we get an exodeviation. And when the patient tells us that the red line seen by the right eye is on the right-hand side, then the patient has an esodeviation. And this is for the vertical. When we combine it with the Thorrington card, we don't need to use prisms in order to measure the deviation because the Thorrington card gives us the prismatic deviation. The Thorrington card has a ruler, and every notch on that ruler is basically equivalent to 1 or 2 prism diopters, depending on the version of the Thorrington card. You know, typically the Thorrington card is used for near, and we used to teach our students that one of the disadvantages of the Thorrington card is that it's only for near. However, I was at UPC, the University Polytechnic Catalonia, where they have an optometry school, and they have a Maddox Thorrington card test on a distance version. They have it posted in their clinics for 3-meter distance. So basically, it can also be used at a distance, just the notches need to be exactly equivalent to 1 prism diopter. The Howell card is very similar to the Thorrington card. However, you don't need the Maddox rod at all, just need polarized lenses. And then one eye views the arrow and the other eye views the ruler. And the patient says where the arrow is pointing, and that gives you the prismatic deviation, the Phoria deviation, without needing to use any prisms. So that's one of the big advantages in using any of these cards, is that you don't need a prism bar in order to measure the deviation. And when you do it with just free space and you hold your pen light and you've got the Maddox rod, you need to also combine it with the prism bar in order to measure the deviation. The Maddox wing also has the advantage that it has the ruler, where every notch is equivalent to a specific prismatic amount, and you don't need to use loose prisms or a prism bar in order to measure the deviation. The patient will tell you where the arrow is pointing, and that will give you the Phoria deviation. However, the Maddox wing does have that disadvantage that it's only meant for 33 centimeters working distance. It also has a disadvantage that it has a permanent ocular that's intended for 60 millimeter pupillary distance. So if your patient has a lot smaller, like children, then it's not going to be an ideal test for measuring Phoria. In addition, a lot of people don't know this, but it was really intended by the manufacturer to be held at 15 degrees inferiorly to simulate reading. And this test is supposed to be conducted both with and without the habitual correction for near. And so the disadvantage of the Maddox wing is this permanent pupillary distance and the fact that it's only for near. The Schober test uses anaglyphic separation, red-green goggles. Because the background is black, the eye with the red filter sees the red plus, and the eye with the green filter sees the 2 green circles. And the patient is asked to state where is the plus with respect to the circles. And if the patient sees the red plus on the left-hand side, then you know that the patient has an exodeviation. And if the patient reports that the red plus is on the right-hand side, you know that the patient has an esodiviation. And also here, you would need to introduce either loose prisms or a prism bar in order to quantify the amount of Phoria. Here on the bottom, I showed you an example of what an orthophoria might look like. But here, look, the background is white. If the background is white, then the eye with a red filter sees the green, and the eye with a green filter sees the red. So the results are a little bit different from how I described previously. This is the polarized cross test. I don't know if you all are familiar with it. It appears in some of the projectors. And this is not a dissimilar image test because both eyes are seeing a similar type of image. However, the right eye sees the upper and the right hand part of the test, and the left eye sees the left and the bottom part of the test. And in order to measure the vertical deviation, then the patient has to tell you whether the 2 horizontal lines are continuous or there's a difference between them. And in order to measure the horizontal deviation, the patient has to tell you whether the vertical lines are continuous or there's a deviation between them. And then you would add prisms until the patient reports that they're aligned. Now, this cross test can either have a central target that's fused or not have a central target that's fused. If the central target is missing, then this test measures the dissociated Phoria. However, If there is a central fusional lock, a target that's seen by both eyes, then this test does not measure the dissociated heterophoria, but rather it measures the associated phoria, which is a completely different concept. The dissociated phoria test, which is subjective, is the von Graff method, in which you place 12 prism diopters base in. Some textbooks say base out. It really depends on which school you go to, which method. And 6 prism diopters base up. And again, some textbooks say base down. It really doesn't matter. This test can be measured either using the step method or the smooth method. Step is when you use either a prism bar or loose prisms to test it, and then it's in free space. And the smooth method is when you use the phoropter. It's considered smooth because when you turn the wheels, the progression of the prisms is much more gradual, so it's considered smooth. However, when you use the prism bar, you use the step method because you're jumping initially between steps of 2, but as you reach higher prismatic amounts, you're jumping between 4 and even 6. In the von Graff, it's really important to make sure that the patient is fixating on the static target that's not moving. So, and then if you're measuring, for example, the horizontal phoria, you'll tell your patient to please look at the bottom target, and then you'll move the prisms until the patient says that the 2 targets are parallel to each other, like headlights on a car. And also here, when you measure the vertical, you want the patient to fixate on the static target and then reduce prisms until the 2 targets are like buttons on a shirt. The cover test, as we mentioned, and the majority of you actually use in your clinics, has 2 parts: the cover on cover, which is used to diagnose whether there's a strabismus or not. And a patient who doesn't have a strabismus is automatically said to have a phoria. It could be an orthophoria, but automatically the patient is said to have a phoria. And then you would use the alternating cover test in order to quantify and state the direction of the phoria. If no movement is detected on the alternating cover test, meaning you don't see the eyes moving, at this point, you're really supposed to ask the patient whether the patient sees any movement, and that's considered phi movement. And phi movement is a subjective way of doing the cover test. And that's usually only used when we're talking about very small amounts of heterophoria. The advantages of the cover test is that it's very cost effective. You don't need any fancy equipment. You just need a target and you need your hand, and you could use that as a cover. It's easy to administer at any distance, and it's very portable. However, it also has disadvantage. It has a very limited resolution. Well, not very, but it's a limited resolution. And the reason it's a limited resolution is because studies show that examiners can only detect movements that are 2 prism diopters or larger. In other words, if your patient has a 2 prism diopter exophoria, it's going to be very difficult for you to notice it. And the same goes for 1 or half a prism diopter. And so often examiners will say that their patient has an orthophoria when in fact the patient might have an ESO or an exophoria that's quite small. The results of this test are also very dependent on examiner experience. And as we'll see later, they're dependent on the occlusion duration. And heterophoria has been shown to only stabilize finally to its final resting position after approximately 5 seconds of occlusion. And most examiners do not cover for a full 5 seconds. They'll do their test faster because of time restraints. So are all heterophoria tests the same? Most studies show the same findings consistently over and over again. So I only brought you 2 studies as an example. This study by Casillas and Rosenfield is from 2006. And they compared a couple of tests. They compared the von Graff test, the Maddox rod test, and the Maddox rod combined with a Thornton card. And they measured it for distance and for near, 40 centimeters. And they measured it both with the phoropter and the trial frame. And they compared all these different methodologies. And here is their final conclusion. In considering horizontal deviations at distance, all 3 techniques showed better repeatability, meaning the results were more consistent when used with the trial frame compared with the phoropter. The Maddox combined with the Thornton techniques used with the trial frame had the best repeatability, and that's consistent in all the studies that I've looked at. Whereas the von Graff procedure, when quantified with a phoropter, was the poorest. And that's also consistent with all the tests. Another thing they state is that the best repeatability was found when using the Maddox rod procedure with a trial frame. And the largest differences between the findings in the different procedures was observed with the von Graff procedure. However, the differences were not that large, only 2 prism diopters. So in summary, the Casillas and Rosenfield study, which again is consistent with all the rest of the studies I've looked at, shows that the von Graff has the worst repeatability, and the Maddox rod combined with the Thornton card has the best repeatability. This study came out in 2021 from the Journal of Optometry, and it talked about the repeatability and reproducibility of 4 techniques for measuring horizontal heterophoria and the implications for clinical practice. So here's their summary, and here we see the coefficient of repeatability. And the closer the coefficient of repeatability is to 1, the better the procedure is. And I've marked for you here the procedures that seem to have the best repeatability, both within the same patient that's measured a couple of times with one examiner, and also between different examiners. So the best method is the Howell card at 33 centimeters, but not at distance. And for distance, the Maddox rod technique seems to have the best repeatability. And for near, the alternating prism cover test seems to have the best repeatability. So these are the key methods that are considered the most reliable methods to use. And as I said before, it's consistently shown that the von Graff is the worst. So now I want to go back with you to examine this question once again. Is the cover test an objective technique? Because we know that it's affected by the clinician's experience. And we know that the examiner's endpoint criteria for what is considered ortho and what is considered exo and what is considered ESO, that may vary between examiners. We also know that the resolution limit sets a low point for all the examiners. We are not able to physically perceive movements that are smaller than 2 prism diopters. So we can't even detect something that's smaller than 2. So is it really an objective technique? And a truly objective technique, one might argue, are eye trackers, because eye trackers can track our eye, they can track our eye under the cover, and the eye tracker will be sensitive to even 1 pixel of movement. So this is an example of an eye tracker, which is a relatively cheap, off-the-shelf eye tracker that anybody can purchase. This is the SMI 250 red, which is 250 hertz. And it uses an infrared technology. So infrared, the advantage is that the visual system is not sensitive to infrared. However, the eye tracker is sensitive to infrared. So what we can do is we can cover the eye with an infrared filter. I'll just show you one. That's me with an infrared filter. And the infrared filter means that only infrared light goes through the filter. I myself under the cover cannot see the light because the visual system, the human visual system, is not sensitive to infrared light. However, the eye tracker, which is positioned over here, is sensitive to the infrared light and can see what's going on with my eye under the cover. So my argument is that this type of a system is a truly objective system. It's not dependent on examiner experience, and it's not dependent on examiner resolution. And it can detect even really minute eye movements. So our research questions in our research study, we had basically 2 different questions. The first was, can we take a simple infrared detector and combine it with an off-the-shelf video-based eye tracker under unrestrained conditions to measure the fully objective heterophoria? And the idea was, if we can do this, we can use a really cheap eye tracker, then basically each one of us clinicians can combine this in our clinics to measure the real eye position of our patients. So that was the first experimental question. The second experimental question was to validate this setup and compare it to the clinical cover test, and then look and see how varying the test conditions, meaning the clinical procedure, could affect the results of the test. And we did that by varying two different conditions. The first was the cover duration. We compared a 3-second cover to a 10-second cover to see if that might affect the results. And the second question was a question that we always say in the clinic, and tell me if you weren't taught this, that it doesn't matter which eye you're looking at under the cover. The right eye under the cover and the left eye under the cover are expected clinically to perform similarly. However, we can't really test this when we perform the test clinically. But when we use an eye tracker, which is combined with an infrared filter, we can actually test and see how much the right eye under the cover moves and how much the left eye under the cover moves, and examine and see if the eye under the cover influences the results of the test. And the results of this study were published in TVST, Translational Vision Science and Technology, back in 2020. And this was our setup. This is me running the experiment. And here you see the eye tracker. And in a second, I'll explain to you why the eye tracker is on this little stand over here. We used this monitor because we wanted to simulate the clinical condition as closely as possible. And so we created a light source on the computer monitor, and we wanted the computer monitor to be exactly 40 centimeters away from the patient. The problem is that the eye tracker, it works optimally when it is 60 centimeters away from the patient. And so in order to do that, we put the eye tracker on its separate holder and we moved it back a little bit. And then we used a screen with a holder that was 40 centimeters away from the patients in order to simulate clinical conditions. We did have a little bit of an issue here because you see the angle of the eye tracker, and we wanted the eye tracker to really capture the eyes. But sometimes when the eye tracker was positioned in a particular location, the screen bothered the eye tracker from measuring. So it was a little bit tricky, but we figured it out and we got it to work. And this is the infrared pass filter, which was used as an occluder. We did something else that was really neat, and we synchronized it with the screen so that when it was directly in front of the eye tracker, it would turn on, and then it would send a ping to the computer program. So the computer program knew exactly when the eye was being covered, and then it knew when to record. And this is what the eye tracker, this is the eye tracker image when I have the occluder in front of the left eye. And this is the eye tracker image when there's no occluder in front of the eye. So this is just like cover, uncover, what you see here. And these are eye traces that we used in order to analyze the data from each one of the participants. So we have, this is the left eye, this is the left eye, this is the right eye, and this is the right eye. And what you see here is an eye trace, and this is over time, and this is pixels. And over here, we have a cover time of approximately 3 seconds. So, you measure for 3 seconds, but in fact, it may not be exactly 3 seconds. And what you see here is that because we use the system that was synchronized with the eye tracker, it counts exactly how long the eye was under the cover. And so when you think you're covering for 3 seconds, it really ended up being 3.18 seconds. So it kind of varies. And then when you think you're covering for 10 seconds, you see that here in this run, it was really 10.8 seconds. And what you see here is that there's a little jump. Do you see that little jump here in the left eye? And there's no jump in the right eye. And that means that the right eye was the eye that was fixated, and the left eye was the eye that had the cover. And you see that jump right after you put the cover in front of the eye. And over here, this is the left eye, and there's hardly any movement in the left eye. That's because the left eye was open, and the right eye had the cover for 10 seconds, and you see the jump in the right eye. And what we did in order to calculate the amount of phoria is we subtracted the left eye position from the right eye position. And then when you subtract it, you see this is approximately 3 seconds of eye position under the cover, and this is 3 seconds of eye position when there's no cover, so it's fusion, baseline. And the difference in pixels in this condition, it was 52. And here in this condition, it was 70. And we translate, just using geometry, 40-second meter distance and the pixel movement, and we can translate that into prism diopters. So how did we run the experiment? First, we wanted to include normal, healthy participants. So after we verified the inclusion criteria, we measured them either with the cover test or with the eye tracker. And this was randomized between the patients. Some patients were measured first with a cover test, and some were first measured with the eye tracker, and vice versa. And then the eye tracker, we had many different conditions, and also those were all run in random order. Either the right eye was covered or the left eye was covered, and the cover duration was either 3 seconds or 10 seconds. And each of these conditions was measured 3 times, and the average was taken. And then we used statistics in order to compare between the different conditions. So we had 30 participants, 11 were male. Their mean age was 24 and a half, and the age range was between 20 and 28. This is their mean decimal visual acuity in Snellen, so almost 1, almost 6.6, almost 20/20. And their near visual acuity was all Jaeger 1+, and the mean stereo was 20 arc seconds. So these were all normal participants. Their heterophoria ranges range between 14 prism diopters of exophoria to 4 prism diopters of esophoria. 12 participants had greater than 4 prism diopters of exo, and 4 had more than 1 prism diopter of esophoria. So this is the results, and this is the mean results for all the experimental conditions. In the cover test, the mean of all the 30 participants was approximately 4 exo plus minus 4 prism diopters. With the right eye covered for 3 seconds, the mean phoria was -3. And with the right eye covered for 10 seconds, the mean phoria was -4. With the left eye covered for 3 seconds, the mean phoria was 3 exo. And with the left eye covered for 10 seconds, the mean phoria was 4 exo. Now look at these numbers. You can already see a trend here. Just when you look at the mean, look at the mean in the cover test and look at the mean under each one of these conditions. You can already tell which cover duration more closely approximates the clinical cover test. And you can also see a trend between when we cover the eye for a shorter amount of time versus when we cover the eye for a longer amount of time. So let's look at the results in terms of the influence of the covered eye. First of all, this is to show you, this is the left eye plotted as a function of the right eye, and there's a high correlation between them. And this is for the 3-second duration, and the same for the 10-second duration, high correlation between them. And what you see here, these are considered Bland and Altman plots. These are plots that look at the difference between the right eye and the left eye as a function of the mean measurement of the right eye and the left eye. And I'll just take another second to explain how these plots of Bland and Altman work. When we want to compare whether the right eye under the cover and the left eye under the cover give you the same amount, if they were exactly identical, we would expect that when we subtract one from the other, the mean difference would be 0. And that's exactly what you see here. The mean difference was 0, both for the 3-second condition and for the 10-second condition. However, each one of these circles represents one participant that participated in the study. And you can tell that not everybody had a 0 difference. People fluctuate around this mean difference of 0. Another thing that we look at in these plots is the 95% confidence intervals, meaning if we take 95% of the observations, what would be the range in which they would fall? And we expect it clinically, since we know that the resolution of the human eye is approximately ±2, we would expect everybody to fall within ±2. And that's true for the 3-second duration. For the 10-second duration, we do have 2 observers that fell outside of the 95% confidence limits. We also used statistics and looked at whether the right eye measurements were significantly different from the left eye measurements, both for the 3-second cover and for the 10-second cover. And the Wilkinson test showed that there were no significant differences between the 2 measurements. We also examined the cover duration, meaning is the 3-second cover the same as having a 10-second cover? So what you see here is the right eye 10-second plotted as a function of the 3 seconds, and we see that it's highly correlated. And the left eye 10-second plotted as a function of the 3-second is also highly correlated. And then also here, in order to compare the 3-second cover of the right eye to the 10-second cover of the right eye, we have Bland and Altman plots. So this is the difference plotted as a function of the mean. And this is for the right eye. And over here, this is for the left eye. Now, we did something else here that we didn't do previously in these plots for the covered eye. We separated the data for the exophores, which is the minus here. This is the exophores. These are the exophores, and this is the isophores in blue. And we separated them because we saw that when we put them all together, we clumped them up together like over here, the behaviors for the isophores and the exophores were very different. So we separated them, green and blue, green exophores and blue are isophores. And what we see when we take the 3-second data and subtract from it the 10-second data, so think about numbers. If I have an exophoria, and this is a particular minus because it's exo, let's say -5, and I subtract from it an even higher exo, let's say -10. So if this was -5 and I do minus of -10, I get an overall positive result. And that's what you see here, which means that for exophores, when their eyes were covered for 10 seconds, we measured a higher exophoria. And the same is true for the isophores, just in the opposite direction, plus, minus, plus. So the 10-second cover duration had a higher isophoria. And what we found was that when we applied the statistical test, there was a significant difference between the 3-second and the 10-second cover duration. So these were the results for covered eye. We saw no significant differences. And these are the results for the cover duration. And we see an effect of the duration of the cover on the results. In addition, we also wanted to compare the clinical test to the eye tracker. And so these are the results for the cover test and the eye tracker under the 3-second eye tracking condition when the eyes were covered for 3 seconds and the 10-second cover duration. So first we see that the data are correlated, are highly correlated. So we can also apply a Bland and Altman analysis here. Now, what you see here is that for the 3-second duration, look how many observations fall outside the confidence intervals. So we cannot say that these two are similar to each other. And also, I'll remind you, when we looked at it in the beginning, the cover test measured a mean of -4, meaning 4 exo. And when we looked at the 3-second eye tracking conditions, they measured 3 exo. So there's a difference there. And that's a difference that you see over here. Approximately 1 exo difference, 1 prism diopter difference. But for the 10-second duration, we do have a few observations outside the confidence intervals, but we do see a nicer trend of agreement between the cover test and the eye tracker. And also the Wilkinson test showed us that there were significant differences between the eye tracker results for the 3 seconds compared to the cover test, but no significant differences between the 10-second eye tracker result and the cover test. Another thing we were interested in seeing was how much variability there is when you repeatedly, right? We took 3 measurements of each condition. So we wanted to see the variability within the 3 measurements. And this is the variability for the 3-second duration of cover. And this is the variability for the 10-second duration of cover. So surprisingly, there was more variability when the eye was under the cover for 10 seconds, presumably because it allows the patient's eye to travel around more and there's less control. We don't know why, but it's interesting to see that with a longer duration, even though it might allow the heterophoria to divert to its resting position, it is more variable. So we do see an influence of the cover duration, where longer cover durations result in higher heterophoria values. And this was not the first time somebody reported that the extent of the cover affects heterophoria. Also, Simon Barnard in his PhD thesis in 1999 showed it. And we think it's because the longer dissociation allows the heterophoria to drift to its final position. And we think that this is important for clinicians to know. So if you're using the cover test, which the majority of you reported that that's what you use, in order to measure heterophoria, you really need to keep this in mind. Because if you do the test really fast, you're allowing less dissociation and you're not measuring the final heterophoric rest position of your patient. In terms of the influence of the covered eye, Pelley and McCormack in 1983 showed an influence of the covered eye only when there's a clear ocular dominance, meaning if you're clearly right eye dominant, then when you cover the right eye, you'll get a different result than when you cover the left eye. However, both our findings and Mestre, who also did a similar study in which they compared, but a fancy eye tracker to the cover test, they did show a difference in the covered eye. However, it was not significant clinically because it was smaller than 1 prism diopter. When we looked at our data for the right eye versus the left eye, for the 3-second cover duration, the difference was just 0.04 prism diopters, which is basically 0. And when we looked at the 10-second cover duration, the difference was 0.12 prism diopters, which is higher than the 3-second condition, but it's still really, really, really small. 0.10 prism diopters, it's nothing. Has no clinical significance. So we conclude that heterophoria can be measured objectively using an off-the-shelf infrared eye tracker combined with a handheld infrared filter, which is synchronized with the video camera. We also conclude that it doesn't matter whether you cover the left eye or the right eye. It does not seem to be clinically significant. However, the cover duration can impact your results. And that's something that we really should standardize, especially when patients are seeing different clinicians and different caretakers. However, our setup was only examined in healthy populations. So we should really examine it in non-cooperative populations and in pediatric populations to see if the results are similar. So that was it. That's what I wanted to show to you and talk to you about today. And I want to thank again, Fakrudin, for inviting me to speak today. And I want to thank our study participants. And I also got a publication grant from our college and the Conference and Research Board.
Well, thank you, Dr. Liat, for that, for sharing that wonderful work which you have been doing and, sharing with us how that work which you have been doing can be applied into clinical practice. That's the most important part where you mentioned that, the duration of the occlusion and which eye to occlude and things like that. These are some things which we really struggle sometimes. And I think the clinicians here would definitely agree that this is something which always sticks into our mind. What should we be doing, right? And we have a research evidence for it now. And I think that can be taken up as the starting point. And when we go out to the clinic, make sure that things are done properly and patients are seen as they need to be. But we have a short video from Aili, who has joined us as our education support for this session. Aili is an app which helps to kind of assess binocular vision as well as help to assess a lot of binocular vision tests, and they are still developing. So we have a short message from the team Aili.
Hello everybody, and welcome to this brief introduction to the Aili app. My name is Francois, and I am an optometrist and co-founder here at Aili. While in practice, we became frustrated with the current testing methods, especially related to binocular vision. There had to be an easier way, so we developed a solution that eases the testing, analysis, and management of complicated eye conditions and instantly enhances the skill set of the modern practitioner. Aili is a tablet app and a complete clinical application in the form of a digital test card, which the practitioner can easily use to record all clinical data, including case history, objective tests, subjective tests, and ocular health while staying engaged with the patient. Our easy-to-use binocular vision tests are all performed on the tablet and makes an in-depth binocular vision exam a piece of cake and accessible to practitioners of all levels, making it simple to implement specialty services into any practice. Some of these binocular vision tests include accommodation flexibility, Phoria, stereo acuity, and fusional reserves. Here is a quick video to show you how you can enhance your clinical testing and service offering in 80 seconds with these tests. A results table will be automatically generated from the test as well as the manual data inputs. The results will automatically be interpreted and compared to age-related norms. We will also generate a graph that will give you a snapshot of the health of the patient's visual system and can be used as a useful communication tool to help illustrate where the patient's visual system is underperforming and might need some help. As part of the reporting feature, an automatic summary and suggestion section are also generated to guide you with the diagnosis as well as the treatment options. If the patient requires vision therapy, then ILI also has a vision therapy module where the patient can do vision therapy on the tablet while the practitioner can monitor it and track results remotely. Some of our latest features include tools to help introduce myopia management to any practice. We help to assess the risk of myopia development and/or progression. ILI also has a built-in actual length estimator, so there is no need to invest in a biometer if you want to start monitoring actual length, which is a key metric to measure and track in myopia management. You can track RX progression. We will also plot the patient's actual length automatically on an actual length growth chart, which again is a useful communication tool to engage the patient or the parent to show where the patient might end up if no management is done, or to track the efficacy of a specific management solution over time. ILI also provides information on the latest myopia management solution based on the latest research and gets updated as new research comes out. Right, so that's ILI in a nutshell. We are constantly exploring and adding features to help make life easier for practitioners. And we would love to hear from you. You can reach us at hello@ili.com with any queries or questions. You can also visit our website, www.ili.com, if you need any further information on pricing and more. We also have a 14-day free trial available, which you can access by completing the registration form at the bottom of the website, and then we will get you going. Right, we hope to see you on the other side. Cheers.
What is the difference between dissociated and associated phoria?
Okay.
So dissociated phoria measures the tendency of the eyes when there is no demand for fusion. However, associated phoria actually measures what happens with the visual system under binocular viewing conditions when there is a demand for fusion. And most visual systems are not exactly pointing on an object. They're a little bit behind with exo fixation disparity, or a little bit in front of with an ESO fixation disparity. In the associated phoria, is the amount of prisms necessary in order to bring the visual axes directly on top of the object in visual space. So we measure that by presenting not only dissociated targets, but also a fusional target. And that way we measure what the eye position is with respect to each other when there's actually a fusional target. However, dissociated phoria is the tendency of the eyes when there is no demand for fusion. So that's completely dissociated. So hopefully that was clear and I answered that question.
Yeah. Great. Thank you so much, Dr. Liat. I'm just going to pull in the next question and we'll just get started on this and we'll take up the questions which come up. One of these, I think most of them you kind of really bit covered during the talk, but just to reinforce because the questions were coming in before you discuss. This one is talking about the reliability and the repeatability of the tests. So again, to reinforce which one.
Yes. So what I said was that consistently we find that the Von graph is the least reliable and the least repeatable of all the Phoria testing, all the Phoria tests, and that the Maddox rod in combination with the Thorrington seems to be the most reliable and repeatable. And in addition, specifically when it's used with a trial frame rather than the phoropter, possibly because the phoropter induces, night myopia, it induces a near effect, an awareness of nearness. So it might induce some convergence, it might induce some accommodation. And the advantage of the trial frame is that you don't have anything attached smack to your face and it's more free viewing. So that would be my recommendation.
Great. Okay. Thank you so much. And I'm just going to take the next question about the eye tracking. And I think you did tell that you had done the experiments in young, healthy subjects. But if we were to use these for special population kids, for cerebral palsy or Downs.
We really do hope that this would be a great solution for non-cooperative populations, because basically you just need them to look at the target. And then the eye tracker just automatically measures everything. However, we do have that little piece with the infrared filter that one would need to put in front of the patient's eye. But, even when you're measuring them in the clinic, you need to do a cover test, you need to cover their eye. So you would need to use some kind of device or your hand in order to cover the eye. So presumably we'd be able to do that so long as the patient doesn't fight the occluder. And then this would be a very objective and relatively quick method of assessing these patients' phoria.
Right. Great. And the other question just related to the eye tracking devices, talking about the inter-manufacturer related standardization problems. So any thoughts over that?
This is a really good point. However, we always, with eye trackers, we have to calibrate them. All eye trackers require calibration. And so assuming that all eye trackers are appropriately calibrated, which means we know exactly where the eye is looking, where the eye position is with respect to the target, and we know the viewing distance, I don't think that would be an issue because, again, these is supposed to be the most objective way. It's just looking at what the eye position is and calculating based on the amount of pixels. Pixel differences between the right and the left eye, how much the eye jumped under the cover.
Right. Correct. And I think somebody did comment on the use of testing for uncooperative patient. We could probably do Krimsky tests.
Well, the Krimsky is a variation in which we quantify using prisms how much the eyes are misaligned with respect to each other using the Hirschberg reflex. Now, the Hirschberg reflex is only to measure tropia. It does not measure phoria because you're not breaking fusion at any point in time. And in addition, one should always keep in mind that the Hirschberg test, you as an examiner are only sensitive to approximately 0.5 millimeter of a deviation of the light in the patient's eye, and that's equivalent to 11 prism diopters. So the Hirschberg, even when you combine it with a Krimsky, is sensitive to very large tropias. It's not sensitive to small tropias, and certainly it does not pick up phoria.
Right. Okay. So I think the best way is to kind of, the eye tracker would be one of the best way, if I may put it that way. Yeah.
Yeah. So we are really hopeful that that could be a promising way of measuring patients' heterophoria in an objective way, picking up very small deviations without having examiner influences.
Yeah. Great. And I think somebody wants to know about the
So
cost
we used a
factor. Yeah.
relatively cheap eye tracker. Our eye tracker was in the couple of hundreds zone. And we're thinking about ways of finding eye trackers that are even cheaper so that it will become something that's really cost effective. But right now, we haven't found anything yet.
Right. Great. Okay. I'm
You have
just
to admit that even a couple of $100 is not a lot, because usually optometry equipment is a lot more expensive than a couple $100.
That's right. Yeah. And why not invest in something which helps us to kind of help patients and monitor? I think most importantly would be to use a test which helps us to monitor the changes or look at them every 3 months and see whether the therapy or the vision exercises which we are giving kinds of helps them objectively. Subjectively, maybe yes, but objectively, we as a clinician, we always like to look at numbers, right?
Right.
So that would be something for the coming future, where we can use these advanced technology for the upcoming monitoring for the patients as well. Great. Okay. And I think one question again which came to me, I'm just going to read that out on the measurement as well. Any preference of the room illumination setting while measuring phoria? Do you have a preferred room illumination? Should it be dim? Should it be bright? Depends on the test.
That's a really good question. Now, if you're doing the Maddox test with the Maddox rod and a pen light, obviously you need to have a very dark room. If you have even a little bit of stray light, that can create additional lines in the perception of the patient, and then it's very difficult for the patient to respond. I think another thing I didn't mention, and I probably should have, is that one of the disadvantages of the Maddox rod test is that because it's not very clear to the patient where to fixate, and you ask them where the line is with respect to the dot, they start chasing the line. And then their fixation goes from the pen light, which is where they're supposed to be fixated, to the line. And then they start like chasing the line, and the line starts moving. And so it's really good to tell the patient to close their eyes, open, and give you first perception. So one of the difficulties with the Maddox rod test in general is the fact that it's really difficult to understand, to explain to the patient what you need them to do, what you need them to say to you. So there's a lot of patient education that goes into that test. And as I said before, you need a really dark room. But when the room is too dark, then you're getting too much dissociation. That also might not be good. And one of the advantages of doing it, doing a cover test, is that you can do it in a dim light. And then it's more similar and more approximates everyday conditions. So also the Van Graaf needs to be in complete darkness. Only the cover test can be basically in dim room. And we did the eye tracking experiment in a dark room.
Right. Okay. Yeah. So that could probably answer that different test requirements are different in terms of testing as well. Another connecting question in terms of testing, it asks that the testings for phoria measurements are usually done for, let's say, 3 meters or 6 meter distance, but most of the time the vision therapy happens at a near distance. Is that something which we practice, and would that be a consideration when we are doing a treatment for phoria? Any thoughts over that?
Can you repeat the question? I'm not sure I fully understood.
Yeah, the testing happens, the phoria testing are said to be done at a particular distance, let's say 3 meters or 6 meters. But
for distance.
Yeah, for most of the vision therapy exercises are for near in terms of phoria vision therapy. So would that have any effect on the results? Any thoughts?
So we are careful, I think, as clinicians to measure our patients' phoria at both distance and near.
Right. Yeah.
And I think the vision therapy exercises that we apply to our patients are applied based on the distance in which we see that the patient is struggling. And we have some therapies that we can do at larger distances. Although the majority of the patients, I think, will have astenopia and complaints when they have issues for near. And I see somebody asked me privately if there's a difference in the measurement of the phoria with or without contact lenses, which is a really interesting question. I would not expect differences with or without contact lenses because the contact lenses are really close to the eye and they have less of a prismatic effect. However, I would expect that there would be some differences, possibly not clinically significant, when a patient is measured with and without their glasses. And even more so if it's an esophoric patient with a tendency to esotropia who's also hyperopic. Then obviously I would expect to have differences with and without the spectacle correction.
Right. Yeah. So I think, again, I'm just going to reinforce your point. So when it comes to testing, make sure that the next time when the patient comes to you and you want to kind of look at whether it's helping or not helping, use the same method, so that you get a good repeatability and use the same way. So first time contact lenses were used, use the contact lenses the second time and don't get shocked what happened, or vice versa, So that's something which is also a clinical message which Dr. Liat had given during the talk, that make sure that what you're doing at the first time, repeat the same thing at the second time to kind of look at. And not all the tests, as you said, are reliable as well. So we have to be very cautious as clinicians to make decisions.
I think as a profession, I know that in America and also in the UK, if I'm not mistaken, they have these guidelines for professionals about how to conduct particular tests for specific populations. And I think we should come together as a profession and kind of come up with guidelines that we all use consistently, because that'll make for better patient care.
Right. Yeah. Awesome. Great. So I think we have taken all the questions which popped up on the chat. So thank you so much once again, Dr. Liat, for doing this session for us and taking us through your work as well as the findings of the results of the research, what you have been doing, and sharing that expertise with us today.
Thank you again for inviting me.
Thank you, everyone, for attending. Thank you so much, Dr. Liat, for spending your Sunday afternoon with us and doing the session for us once again.
Thanks again. It was a lot of fun.
Take care. Take care, ma'am. So take care, everyone. We do have session planned next week and through the rest of December. We have, I think, about 2 to 3 sessions in plan. So we will share the details of the sessions to you. Until then, take care, be safe, and hope to see you in the next session. Bye-bye.
Bye.
Bye.